All right, so hello everyone. My name is Luke Boegner. I'm a research scientist at Peraton Labs. And this talk I'm going to be sharing some of the work that I did with my colleagues at Peraton Labs as well as colleagues at the Laboratory for Telecommunication Sciences. So the title of this talk is Open Source Large Scale Radio Frequency Machine Learning Dataset, Toolkit and Models. Just a quick disclaimer is that it should probably read almost open source. So we're still looking for one more checkbox for getting this work released. It should be any minute now, though. So hopefully we at least have some things for you to look forward to. So on the agenda today, I'm going to focus in on narrowband radio frequency machine learning. So this is kind of, we're adopting the standards of narrowband versus wideband RFML that's been in several works in the literature, where narrowband RFML focuses in on signals that have already been kind of extracted, isolated, coarsely basebanded, versus wideband RFML, where we might be doing tasks that involve multiple signals that may or may not be overlapping in time and frequency. So for this talk, we're focusing on narrowband RFML, and in particular, there's three pieces that I want to talk through. The first one is the SIG53 dataset that we're introducing. The second piece is TorchSig. It's the soon-to-be open source machine learning toolkit for complex signal processing. And then I want to end with some signal classification results. So just kind of share some results that we've put together with using the SIG53 dataset and the TorchSig toolkit. So jumping into narrowband RFML, in particular the dataset, I just want to start off by kind of setting the stage for why we're introducing a new dataset. And to do that, we kind of need to start with the existing datasets that are out there. So anyone who's done any RFML research already is probably familiar with the RadioML datasets. So these were first introduced in 2016 and then later revised in 2018. And they can kind of be seen as the seminal RFML datasets. These works, along with some papers back in 2016, were kind of seen as the catalyst for the entire application of deep neural networks to the RF world. So since we're now towards the end of 2022, one thing that we're finding is that the ML model research seems to be outpacing the dataset capacity of these initial RadioML datasets. So something that's not shown here, but we have in the paper that we submitted along with these slides that I invite you to take a look at, is some empirical results that are showing this limitation with the dataset capacity. So we took some of these modern neural network architectures, for example, EfficientNet, which is a common architecture in the computer vision world that has some built-in scaling. So there's a B0 meta architecture, and it scales up to B7, and there's even been more work to increase the scale even further, where the scale in the CV world, as you scale up the model complexity, generally improves model performance as well at the cost of additional computations. So one thing we wanted to see was, do these scaling properties still exist with these RadioML datasets? And what we found was, even at the very minimal scale, the EfficientNet B0, the smallest of this modern neural architecture, we were immediately overfitting on these initial datasets. And even once we applied a pretty heavy set of data augmentations, we would still see some overfitting, and we would see that even with this performance scaling across the B0 to B4 architectures, the performance did not change at all. So kind of lending itself to some empirical findings showing that we're kind of at the dataset capacity for these previously introduced datasets. So this leads us into the SIG53 dataset that we'd like to introduce. The SIG53 dataset that we're showing is a new dataset primarily for RF machine learning tasks that has over 5 million data samples or data examples that we pre-split into 4 subcategories or 4 sub-datasets in the clean training, clean validation, impaired training, and impaired validation. So part of this pre-splitting can really help with standardizing both collaborative and competitive performance comparisons from different architectures from different companies, different research institutions, et cetera. As you might have guessed from the title, SIG53, we are introducing 53 signal classes within this dataset. Within these 53 classes, they all come from the same 6 modulation families. So one thing that I'm showing on the slides here is just one example or one signal class from each of these families, where we have an ASK family, a PAM family, a PSK, QAM, FSK, and OFDM. So then across all of these different modulation families and signal classes, we also have increased impairment diversity, moving from the RadioML datasets to the SIG53 datasets. So we, at generation time, apply a randomized set of a slew of different impairments that are realistic to conditions you might find in an RF environment. These might be on the system impairment side or the wireless channel side. And then finally, the thing that I think is arguably the most important and will be done very soon is that this data set is going to be completely open source. So by this, what we're doing is sharing the generation code for how you can generate this code locally. This makes this data set easily reproducible and customizable. So if you have any specific tasks that you might not be as interested in comparing back to our performance on the impaired validation set, but maybe you have some domain-tailored application that you want to use this data set for, you can customize it since we're planning to open source this code. And then finally, it's also reviewable. So another critical piece of this data set that the open sourcing buys us is that the community can review it, can make changes to it, and just verify that everything lines up with their specific applications. So the way that we're doing the open sourcing of this data set is through TorchSig. So TorchSig is our soon-to-be open source signal processing machine learning toolkit. And really what we're trying to do with TorchSig is kind of fill in a blank that we've seen when investigating just the whole the whole machine learning landscape. So anyone who's familiar with like the vision world might be more familiar with the Torch Vision toolkit, or in the audio world, there's the Torch Audio toolkit. And something that we were finding was that there isn't really a full-fledged toolkit for applying these different ML techniques to the complex waveforms or the RF space. So we're introducing TorchSig as a Python-based toolkit that mirrors a lot of the best practices from these other PyTorch libraries. This toolkit, like I said, is capable of generating the SIG53 dataset. We also include some dataset wrappers such that if you're doing existing work on the RadioML datasets, you can continue doing this work, but still get access to a lot of the features and data handling pipelines that we're introducing as part of TorchSig. And additionally, you can build your own custom RF datasets just by following our dataset class templates. So whether this is a synthetic dataset that you're modeling your particular signals, or if you wanted to wrap existing datasets that are file-based, whether that be SIGMF-based file datasets or any other file format. One of the biggest benefits of TorchSig is the fact that we're introducing over 50 domain-tailored data augmentations. So within machine learning, the CV world, the audio world, NLP world, they've all kind of seen that data augmentations are pretty critical for a machine learning training pipeline. So what we did with TorchSig is we've built out over 50 domain-tailored data augmentations. So I've pictured a few here where we just have like a spectral inversion data augmentation where you can see the frequency is flipped. We have an IQ imbalance transform. It's probably a little difficult to see on the slides, but we have like the original constellation diagram, and then it's been amplitude, phase, and DC offset augmentations applied. And then on the bottom, we have a randomized resampler, so that can go up or down from the original data. And with all of these changes, we're dynamically updating the label information with any of these updates as well. So while I said that this talk is focused on the narrowband RFML side, if you were doing a localization in time and frequency task, the labels with the spectral inversion would be followed, for example. So just a few examples of some augmentations that I've shared here. But on top of that, we also have a slew of expert feature transforms. So everything from the data augmentation side works on complex INQ data. However, a lot of machine learning architectures expect real valued inputs. So we have these transforms that can map the complex components to channels, or you can do a DFT transform or a spectrogram transform, such that you can still get access to all of the transforms that and augmentations that act on the IQ world, but then feed your model data that's been already transformed to the format that your model expects. So the next step naturally is to verify that the SIG53 data set is a sufficiently challenging problem that overcame some of the limitations that we saw earlier on with the existing data sets. So to do this, we started off by taking that same efficient net architecture that I named before and training up 3 different scales, B0, B2, and B4, on the SIG53 data set. And with this, we have the blue circle dots in the top left, where we can now clearly see that with the increased complexity in terms of flops and parameters, we are getting increased performance as well on the SIG53 data set. So this is giving us a good feeling that this data set is sufficiently challenging and complex for these modern neural architectures. Additionally, something that has kind of shown a lot of progress in the machine learning field since a paper that came out in 2017 is the application of transformer architectures. So we wanted to not only try out an efficient net, which is a convolutional-based architecture, but we wanted to try out a transformer architecture as well to see do these performance gains still happen on the RFs and complex signal space. So in particular, we picked the cross-covariant image transformer, so that's EXIT here. And pretty much we just chose this one because it has linear complexity with respect to the input sequence size. So we get a little bit faster performance with this transformer as opposed to the vanilla transformer that was originally introduced in 2017. So EXIT also has some built-in scaling properties. So we just picked the smallest 2 scales, EXIT Nano and EXIT Tiny 12, and tested this again on the SIG53 data set. And once again, we saw performance scaling with the model scaling. And interestingly, these EXIT models did outperform the efficient net models on the SIG53 data set. So the same performance gain that's happened in the computer vision and the NLP world seems to be holding true, at least on the SIG53 data set. Additionally, we were getting accuracies in the 60 to 70% range. So it seems like this was a good knee in the curve for presenting a data set that's sufficiently challenging but has room for improvement as well. Following these experiments with the SIG53 data set, just to the plain vanilla static SIG53 data set, we wanted to really evaluate how the torch SIG augmentations could further improve our performance. So on the bottom left, we have some results for taking the performance on the static data set, but then now applying these data augmentations during training time. So each time these samples are requested from the SIG53 data set, we're applying new out-of-distribution data augmentations that were intentionally from a different set of those used in the impairment selection that we used in the generation of the SIG53 data set. And as you might expect with these additional augmentations, our performance is increasing effectively for free because we're just applying these existing augmentations at training time and then seeing this increased performance by roughly 1 to 1.5% across both the efficient net and the EXIT architectures. As one final step, since the torch SIG toolkit is capable of generating the SIG53 data set, we did what we're calling here an online experiment. So this online experiment is, rather than pulling from the static previously generated SIG53 data set, since torch SIG gives us all this generation already, we can just continue evaluating against the static impaired validation set. But at training time, we can, on the fly, create new samples. So what this is effectively giving us is an infinitely sized data set that's only limited by the amount of training time that you have to put towards training these networks. And once again, as you might expect, we did see increased performance, particularly with the efficient net architecture. So this is an intuitive result that's just nice to see carried through with these experiments. And then one final figure here on the bottom right is a plot of the validation loss versus the training loss. This is for the, in the blue circles, the efficient net B4 architecture with just the static SIG53 data sets. The red diamonds are with the augmentations, and then the green squares are with the online data set. And what you can kind of see with the blue circles is at one point we get like a little bit of a plateauing happening in the bottom right, where the validation loss seems to kind of stop learning, but the training loss continues. So this is just like your classic case of the B4 architecture starting to overfit. But once we introduce these augmentations or the online data set, you can kind of see how those lines snap back down to a linear relationship so that we can kind of show the power of how the TorchSig augmentations and the online data set kind of can overcome data limitations that your model might be hitting with these overfitting issues. So we additionally did some performance analysis across a few different metrics, where on this slide I just am walking through a few of them. The top left figure is showing the SNR versus accuracy curves for the 5 different architectures that we experimented with. And from the bottom to the top, we have pretty much the smaller efficient net architectures scaling up in size, and then the exit architectures again scaling up in size. And what's interesting here is that a lot of the performance gain that we can see in this plot happens at the high SNRs. So what this is saying is that the SIG53 dataset is a sufficiently challenging dataset even at the high SNRs. So there's still enough complexity in disambiguating these different signal classes, even when there is a very high SNR, a very clean signal. At the top right, I am plotting some accuracies across modulation families. So what you might expect to play out here seems like it is for the most part, where FSK is appearing to be the easiest signal for the networks to classify, while the QAM signals are definitely the hardest. So you can kind of think intuitively how the higher order QAM signals are much more difficult to disambiguate, particularly for the lower SNR signals. So once again, just an intuitive result that is nice to see play out with the actual results we're finding. And then finally on the bottom, I have the modulation family confusion matrices, where we take all the 53 signal classes, collapse them down into just the 6 modulation families. So once again, a pretty intuitive result where these findings are rock solid across disambiguating the modulation families, which means that most of the errors that are coming in with these models are distinguishing the different orders of intra-family signal classes. And then here I just have two pictures for the full signal classes. This is across all 53 classes within the SIG53 dataset for efficient FB4 and the exit tiny 12 architectures. So you can kind of see there is that rough diagonal going down the full class list, as you like to see. It's probably a little difficult to see in the slide setting, but I invite you to check out the paper that we've submitted as well that you can find on the GRCon website. But there are some patterns to the errors that are being presented with these confusion matrices, which kind of verifies the previous claim where most of the errors are happening at the intra-family scale, just having difficulty disambiguating the same families but different orders. Around the midpoint, you can kind of see where the line gets a little bit darker. That's where the FSK families come into play. And you can see how that line stays dark going diagonally down, but then the errors at the higher order FSKs start coming in. And then for OFDM, the subclasses within OFDM are related to the number of subcarriers. So again, you can kind of see how most of the errors here are within different subcarrier counts within the OFDM family. So that about wraps up the talk. I just wanted to kind of end with a challenge to the community. So once this toolkit and the SIG53 dataset go live, I'd like to invite anyone who's interested to try to see if you can beat our performance on the SIG53 dataset. By open sourcing this code, we're really hoping to get some community engagement and see if we can together as a community bring up the whole field of RF machine learning. And then part of that is also sharing your results back with the community. So we're trying to be very open with eventually sharing the TorchSig and the SIG53 dataset and toolkit. So if you could see how you can perform with our datasets if you're interested in RF machine learning tasks, and then kind of feed that back into the community, that would be really great. We currently have a workshop scheduled for Wednesday for TorchSig. We're hoping to get the code released in time for that, but definitely monitor torchsig.com for any updates if that's going to be able to get that out in time, and we'll make an announcement here as well. It wouldn't be a GRCon talk if I didn't put a plug saying that we're hiring both Peraton Labs and LTS. So if you're interested in RF machine learning or contributing to open source or both, feel free to reach out to me or any of my colleagues. And then just one final comment is that this work was funded by the Lab for Telecommunication Sciences. So with that, that about wraps up, and I think I have some time for some questions.
Yep, you definitely have time for questions. The internet is very happy to hear about the open sourcing of it, and they are waiting anxiously. Do we have any questions from the room? I see a question from the room. Excellent.
Yeah, thank you for a great presentation. So is TorchSig like Torch Vision and Torch Audio in that it's built on top of PyTorch, but it has like, special data classes that's, domain specific, but for signal processing, and then also domain specific models for signal processing, just like how in Vision you would have, classes to load the data for certain types of image classification data sets, and then they will have like deep lab and other kinds of like image specific models. So is that what TorchSig is? Or like, yeah, is that a correct understanding?
Yeah, it's we do definitely try to mirror the best practices from the Torch Vision and Torch Audio toolkits. We even are trying to build, or we even have the model API based off of how those Torch Vision in particular, those model APIs work. So the results that I have shown here, we do have built into TorchSig, where you could just do like the model API call to pull down the model architectures. And then you could even change the number of classes, just like Torch Vision for a signal class, or for a vision classification, or a signal classification task. We try to limit the amount of times that we're inheriting directly from PyTorch classes. There are still some cases where we do inherit from them, so that is currently a dependency, I believe, of the TorchSig toolkit. But the dataset classes themselves, we have our own, pretty much it's like a signal data object that kind of carries around the data for all these different tasks and transforms and everything. So that's how we kind of standardize the data processing pipeline, so that as a new transform is built, we can make sure that not only the data, but the label information is updated as well with these transforms. Does that answer your question? Okay, cool.
Do we have other questions from the room? Okay, I think you have completely whacked us with a glue stick. Thank you so much. Let's give a round of applause.